The universe has a speed limit, and it seems absolute. For over a century, Einstein's theory of relativity has told us that nothing can outrace a beam of light. This rule is woven into the fabric of reality itself, a cosmic law that has grounded our dreams of reaching the stars. But what if we have been reading the signs all wrong? By the end of this, you will see the fundamental laws of physics in a completely new light, understanding not just what they say, but what they might allow. We are going to question if that ultimate barrier is a permanent wall or a complex lock waiting for the right key. We will explore how the fabric of spacetime might be bent, not broken, and peer into realms where particles might already be playing by different rules. Does our hunger for the stars reveal a fundamental misunderstanding of the universe's deepest blueprint? At the very heart of this cosmic speed limit lies a pair of elegant ideas. They are the twin pillars upon which Einstein built his revolutionary vision of the universe. First, the laws of physics do not play favorites. Whether you are standing still on Earth or cruising in a perfectly smooth spaceship, the fundamental rules of nature look exactly the same to you. This principle of relativity is a powerful statement of cosmic democracy. The second pillar is the one that truly reshapes reality. It states that the speed of light in empty space is a universal constant. It is the same number for everyone, no matter how fast you are moving or in what direction. This is far more radical than it sounds. If you chase a beam of light in a rocket at 99% of light speed, you will not see it crawling slowly ahead of you. You will measure it racing away from you at the exact same full speed, as if your tremendous velocity meant nothing at all. This constancy is the linchpin. It forces a profound reconciliation between our concepts of space and time. They are no longer separate stages upon which events unfold. They are woven together into a single, flexible fabric called spacetime, and the speed of light is the immutable thread that stitches them together. The mathematical language that describes this weaving is found in the Lorentz transformations. These equations reveal the astonishing consequences of living in such a universe. As an object's speed increases, time for that object slows down relative to a stationary observer. This is time dilation. Simultaneously, the object's length in the direction of travel contracts. This is length contraction. These are not optical illusions or mechanical failures. They are genuine, measurable distortions of spacetime itself, all to preserve that one sacred constant, c. Here, c transforms from a mere speed into something deeper, a fundamental conversion factor. Just as the number pi relates a circle's circumference to its diameter, the speed of light relates distances in space to intervals in time. It is the ultimate exchange rate of the cosmos. This elegant framework seems to build an impregnable wall. If you try to push an object to light speed, the equations show its mass effectively becoming infinite, the energy required becoming infinite, and time for it coming to a standstill. To go faster than light appears mathematically nonsensical within this structure. It would demand imaginary numbers, quantities involving the square root of -1, entering our descriptions of reality. More disturbingly, it could unravel causality, potentially allowing an effect to happen before its cause in some frames of reference. The logical and mathematical case seems airtight. Yet the very strength of this foundation invites a deeper question. Are we looking at a permanent prohibition, or are we simply observing the limits of a particular map? The equations of special relativity are a breathtakingly accurate map of reality at high speeds, but every map has its boundary. To see if a path exists beyond the edge of the chart, we must examine the terrain it describes with even greater care. The mathematical heart of this prohibition is a deceptively simple formula. It is called the Lorentz factor, and it is the precise mechanism that warps reality at high speeds. Represented by the Greek letter gamma, this factor is the mathematical key that unlocks time dilation, length contraction, and the relativistic increase in mass. Its calculation depends on just two things: the object's velocity and the speed of light. At everyday speeds like that of a car or a rocket, gamma is almost exactly 1. Time, length, and mass appear perfectly normal, but as velocity climbs, creeping ever closer to that ultimate constant, something dramatic happens. The denominator of that equation shrinks, and the value of gamma begins to swell. It does not just increase, it skyrockets. At 99.9% of light speed, gamma is about 22. Time for that traveler slows to a crawl, their length contracts severely, and their effective mass multiplies. Push the hypothetical speed even closer to the limit, and gamma races toward infinity. This is the mathematical singularity, the point where the equations break down. To reach exactly light speed would require dividing by zero, a mathematical impossibility. This infinite gamma translates to a demand for infinite energy to achieve that final push, and an infinite mass to move. It is this unforgiving climb to infinity that is so often held up as the final, unarguable proof. Faster than light travel is not just difficult, it is mathematically forbidden for anything with mass. Yet this powerful argument contains a quiet, almost hidden assumption. It presumes the object in question is what physicists call a massive particle with a real rest mass, traveling through the flat, uneventful spacetime of special relativity. The infinity is not a universal condemnation, but a very specific result of a very specific set of rules. What if we are not talking about pushing a rocket through empty space? What if the object itself is not like any matter we know, or the space it travels through is not flat but engineered? The singularity might not be a stop sign on a straight road, but a signal that we have reached the edge of the map. To go further, we must consider whether the road itself can be changed. This mathematical boundary is not a solid wall, but more like a one-way mirror. The equations of special relativity do not explicitly erase the possibility of particles that exist solely on the other side. They simply state that nothing from our familiar world can punch through from here to there. This subtle distinction gave physicists a tantalizing loophole to explore, leading to the ghostly concept of tachyons. Imagine a particle not born in our realm of slower-than-light travel, but one that emerges into existence already moving faster than light. For such an entity, the cosmic speed limit is not a barrier above, but a floor below. It can never slow down to light speed, just as we can never speed up to it. The mathematics accommodating this idea is strange but consistent. It assigns these hypothetical particles a rest mass squared that is a negative number, a mathematical oddity that flips their behavior entirely. In the tachyon's realm, adding energy would not make it go faster. It would make it slow down, approaching the light speed barrier from above. More unsettling is the implication for time. The equations suggest that for a tachyon, cause and effect could be reversed, with an observer potentially seeing its effect before its cause. This is not a flaw in the math, but a direct consequence of allowing superluminal travel within the framework of relativity. While decades of searching have turned up zero evidence that tachyons are real, their theoretical existence is a profound clue. It tells us that Einstein's theory is not inherently opposed to faster-than-light phenomena. Instead, it paints a universe divided into two separate domains, the subluminal world we inhabit and a superluminal world we cannot access. The speed of light is the impassable frontier between them. The true prohibition, then, might not be on the speed itself, but on the act of crossing that luminous frontier. This shifts the question from how to break a law to understanding the nature of the border itself and the consequences of even attempting a crossing. The most terrifying consequence of breaking the light barrier is not a wall of infinite energy, but a tear in the logical order of the universe itself. This is the problem of causality, the idea that a cause must always come before its effect. It is the fundamental sequence that gives our reality its arrow of time and its dependable structure. Within Einstein's framework, this order is protected by a beautiful and precise geometric concept called the light cone. Picture a single event, a flash of light in the darkness of spacetime. That light expands outward in all directions at the speed of light, forming a four-dimensional cone that defines the absolute limits of influence. Inside the forward-pointing cone lies every point in spacetime that the event can possibly affect, its possible future. Inside the backward-pointing cone lies every point that could have possibly caused it, its absolute past. Anything outside these cones is causally disconnected, separated by a gulf that not even light can cross. This structure is the guardian of cosmic sanity, ensuring that causes always lie in the past light cone of their effects, now introduce faster than light travel. It acts like a cosmic shortcut, allowing a signal or object to leap from one point to another without passing through the intervening space at a slower speed. In some carefully chosen reference frames, a physicist with the right moving vantage point could observe that signal arriving before it was ever sent. The effect would literally be seen before the cause. This opens the door to paradoxes that are not just confusing, but logically impossible. The classic example is the grandfather paradox, where a traveler uses an FTL machine to go back and, through some chain of events, prevents their own grandfather from meeting their grandmother. If they were never born, how could they have taken the trip in the first place? The universe seems to have a zero-tolerance policy for such logical knots, which is why many physicists view any mechanism enabling superluminal travel as fundamentally forbidden. It is not an engineering challenge, it is a violation of the most basic rule that keeps reality consistent. Yet this powerful argument, like the energy barrier, rests on assumptions. It assumes that spacetime is flat and featureless, like a vast, empty plane. But what if the stage itself is not flat? The light cone is drawn on the fabric of spacetime. If that fabric can be curved, folded, or reconfigured, then the geometry of cause and effect might be more flexible than it first appears. The prohibition may not be on moving faster than light through space, but on disturbing the deeper, topological rules that keep causality intact. To find a path forward, we must stop trying to outrun light on a flat plane and start thinking about shaping the terrain beneath our feet. The fabric of spacetime is not a static stage, it is a dynamic and living entity. This is the monumental shift introduced by Einstein's general theory of relativity, where his earlier work described the laws of physics on a flat, unchanging background. General relativity revealed that mass and energy do not merely sit upon this stage, they actively shape it. A planet or a star warps the spacetime around it, creating what we perceive as gravity. This is not a force pulling across a distance, but the curvature of the stage itself, guiding objects along the most natural paths through the bent geometry. Within this richer, more flexible reality, the prohibition against locally exceeding light speed still stands firm. You cannot outpace a light beam in the space immediately around you. But the stage itself can be bent, folded, and reconfigured in ways that offer a breathtaking alternative. Imagine the universe not as a flat sheet of paper, but as a folded one. 2 points that are immensely far apart on the flat surface could be brought nearly touching by a fold. A wormhole, or an Einstein-Rosen bridge, is the theoretical realization of this fold, a tunnel or shortcut connecting two distant regions of spacetime. The crucial distinction here is one of path, not speed. A traveler passing through a stable wormhole would not be moving faster than light through the space inside the tunnel. They would be taking a radically shorter route. To an outside observer watching a light beam take the long, curved path through normal space, the traveler would appear to have arrived at their destination faster than light. The cosmic speed limit is not broken. It is masterfully sidestepped by redefining the very geometry of the journey. This is the essence of the misunderstood, a clever circumvention of a law by operating within its deeper principles. Yet this theoretical shortcut comes with a profound engineering challenge. The immense gravity of any massive object naturally crushes such a tunnel shut instantly. To hold a wormhole open to make it traversable would require threading it with something truly bizarre, exotic matter. This is not just unusual material, but a substance that theoretically possesses negative energy density, effectively creating a kind of anti-gravity or repulsive force to keep the throat from collapsing. Whether such matter can exist in stable, macroscopic quantities is one of the great unanswered questions in physics. It sounds like pure science fiction, but to dismiss it is to ignore where our search must lead next. The bizarre requirements of wormhole engineering point us away from the vast cosmos and into the frenetic, probabilistic realm of the impossibly small, to the quantum foam that may be the universe's most fundamental substrate. The universe at its most fundamental level is anything but quiet. Empty space, the void between stars, is not a true void at all. Quantum field theory paints a picture of a seething, probabilistic sea known as the quantum foam. Here, pairs of virtual particles and their antiparticles constantly wink into and out of existence, borrowing energy from the vacuum itself for fleeting moments before annihilating and repaying the debt. This is not mere speculation. We can observe its ghostly fingerprints in a real, measurable phenomenon called the Casimir effect. Imagine two perfectly smooth, uncharged metallic plates placed parallel to each other in a perfect vacuum, brought incredibly close together, separated by a gap smaller than the width of a virus. Something strange happens. An inexplicable force pulls the plates together. The reason lies in the quantum sea. The gap between the plates is so narrow that it can only accommodate virtual particles of certain wavelengths. The wider space outside the plates allows for all possible wavelengths. This imbalance in quantum activity creates a subtle pressure, pushing the plates inward. The energy density of the vacuum between those plates is actually lower than the energy density of the undisturbed vacuum outside. In a very real, laboratory-tested sense, the region between the plates exhibits negative energy density. This is a staggering revelation. That exotic matter with negative energy, the very substance we theorized could prop open a wormhole throat against the crushing force of gravity, is not a forbidden fantasy. It is a legitimate, if minuscule, feature of our quantum reality. The Casimir effect demonstrates that the universe's own rulebook permits the existence of the exotic ingredients required for spacetime engineering. The challenge is one of scale. The amounts of negative energy we can generate are vanishingly small, confined to microscopic gaps and lasting for inconceivably brief instants. To stabilize a wormhole large enough for even a single atom, let alone a spacecraft, would require harnessing and concentrating these quantum effects on a monumental level. It is like discovering that a single drop of water proves the concept of an ocean, then being tasked with moving a continent using only an eyedropper. The principle, however, is no longer just a line in a speculative equation. It is etched into the fabric of reality at the smallest scales, whispering that the universe's most dramatic shortcuts might be written into its finest print, waiting for a civilization with the patience and ingenuity to learn how to read it. The quantum foam suggests the ingredients exist, but the recipe for a cosmic shortcut remained unwritten. Then, in 1994, a physicist named Miguel Alcubierre performed a breathtaking act of mathematical imagination. He asked a simple, radical question within the strict language of Einstein's own equations. What if, instead of moving a ship through space, you moved the space itself? The answer was the theoretical blueprint for a warp drive. Alcubierre's solution describes a remarkable structure, a warp bubble. Picture a spacecraft sitting comfortably inside a pocket of perfectly normal, flat spacetime. This is the passenger cabin. Now, imagine the fabric of the universe directly in front of this bubble being violently scrunched together, while the spacetime directly behind it is dramatically stretched apart. The bubble and the ship within it is then carried along this wave of distorted geometry like a surfer on a cosmic tide. The crucial detail is this. Locally, inside that pocket of calm, the ship is motionless relative to its immediate space. It experiences no acceleration, no time dilation, no relativistic mass increase. It is simply riding a moving hill of spacetime. To a distant observer watching from outside the bubble, however, the entire structure could appear to be moving faster than light, because the destination is being pulled closer by the contracted space ahead, and the point of origin is being pushed farther away by the expanded space behind. This is not a violation of relativity, but its most ingenious application yet, a masterclass in metric engineering. The speed limit is not broken. The road is simply made shorter in front of you and longer behind you. Yet to create this wave, to bend spacetime in such a deliberate and extreme way, requires something to push against the universe's natural tendency to remain flat. Once again, the equations point to the necessity of exotic matter with negative energy density. This hypothetical material would form a rigid ring around the bubble, shaping the spacetime geometry like a lens. Alcubierre's initial calculations for the energy needed were cosmically absurd, requiring the equivalent of converting the mass of entire galaxies into pure, engineered exotic matter. It seemed like a beautiful mathematical curiosity, nothing more, but science has a way of refining even the most outlandish ideas. In the years since, other researchers have tinkered with the geometry of the bubble itself. By changing the shape from a simple ring to a thinner, more dynamic torus, or by oscillating the warp field, some models suggest the exotic energy requirement could be lowered dramatically, perhaps to something on the scale of a large planet or even a small moon. While still far beyond our capabilities, this shifts the conversation in a profound way. The question is no longer whether the laws of physics forbid it, but whether we could ever gather and control the staggering forces required to bend the stage of reality itself. The Alcubierre drive transforms the dream from a question of speed to a challenge of supreme cosmic engineering. Black holes represent the ultimate victory of gravity, places where spacetime is curved so severely that not even light can escape. At their very core, according to the equations of general relativity, lies a singularity, a point of infinite density where our understanding of physics simply stops. The math breaks down and predictability vanishes. It is a tear in the fabric of reality itself. Yet we never see these raw singularities. They are always hidden from our view, buried deep within the absolute darkness of the event horizon. This is not a coincidence. The brilliant physicist Roger Penrose proposed that nature itself enforces a rule he called the cosmic censorship hypothesis. The idea is elegant and profound. The universe has a deep aversion to naked singularities. An event horizon acts like a cosmic curtain, forever shielding the chaotic infinities at a singularity's heart from the orderly universe outside. This censorship is not just about tidiness, it is about preserving causality and the very predictability of physics. If you could stand outside a black hole and peer directly at a naked singularity, the normal flow of cause and effect could become meaningless. The future could become impossible to calculate, so the hypothesis suggests the cosmos always wears a cloak, ensuring these ultimate breakdowns remain hidden from view. This idea casts a long shadow over any faster-than-light scheme that relies on extreme spacetime geometry. Some of the most speculative models for warp drives or theoretical time machines involve creating or manipulating spacetime structures with properties akin to singularities. incredibly sharp curvatures that could, in principle, be used to forge shortcuts. If cosmic censorship is a fundamental, unbreakable law of nature, then any attempt to build such a device might be doomed from the start. The moment your engineering started to create a useful, traversable curvature, the universe might automatically cloak it behind an event horizon, rendering it useless as a shortcut, or worse, catastrophically dangerous. It would be like trying to forge a key from a material that instantly melts in the lock. The censorship becomes a universal veto, a deeper principle that overrules even clever mathematical workarounds. But here is the crucial twist: cosmic censorship remains a hypothesis. It is a compelling argument from elegance, but it has not been proven as a law. The mathematics of general relativity does, in certain extreme scenarios, allow for the theoretical possibility of naked singularities to form. Furthermore, the line between a destructive singularity and an extremely sharp, but controlled and finite, spacetime curvature is a blurry one. Could we, in theory, engineer a warp bubble or a wormhole throat that bends spacetime to an incredible degree without triggering the universe's censoring mechanism? Could we create a structure that has the useful geometric properties we need without crossing the threshold into true, law-breaking infinity? This is one of the most active and contentious frontiers in theoretical physics. The debate between impossibility and mere instability continues. It suggests that the ultimate limit on our cosmic ambitions may not be a simple sign that says no faster than light travel. It might be a far more subtle and active principle, a cosmic immune system that reacts to protect the logical order of reality from our most audacious manipulations. Our journey has brought us to the very edge of modern physics, to a chasm that splits our understanding of reality in two. On one side stands the grand, geometric vision of general relativity, masterfully describing the dance of planets and the curvature of spacetime itself. On the other side thrives the bizarre, probabilistic world of quantum mechanics, governing the frantic dance of particles and forces at the smallest scales. Each theory is spectacularly successful in its own domain, yet they are fundamentally, stubbornly incompatible. Their mathematical languages clash, and their core concepts seem to describe different universes. This is not a minor disagreement, it is the central crisis of modern physics. For over a century, this divide has persisted, a silent fault line running through our comprehension of the cosmos. And it is precisely at this fault line where our question about faster-than-light travel may find its ultimate resolution. The speed of light as a limit is a concept born from the classical, smooth continuum of spacetime described by relativity. But quantum mechanics suggests that at the very smallest scales, this smoothness dissolves into a seething, grainy foam. So which picture is true? The quest to answer this has led physicists to pursue the Holy Grail, a single, unified framework known as quantum gravity. This theory would not just combine the two, it would rewrite our understanding of reality's most basic ingredients. Leading candidates like string theory or loop quantum gravity propose visions that are almost alien to our everyday intuition. In string theory, the fundamental entities are not point-like particles, but unimaginably tiny, vibrating strings. Their different harmonies give rise to every particle and force we know. In this view, spacetime itself may not be a fundamental stage, but an emergent phenomenon, a kind of collective behavior of these deeper entities. Loop quantum gravity, on the other hand, suggests that space itself is not continuous, but woven from a fabric of finite, discrete loops. Picture the universe not as a smooth sheet, but as a tapestry made of individual threads. At the incredibly tiny Planck scale, a distance so small it defies imagination, this granularity becomes apparent. In such a radically different reality, concepts we hold sacred begin to blur. Locality, the idea that objects are only influenced by their immediate surroundings, might be an approximation that fails. Causality, the unbreakable chain of cause and effect, might have a more complex quantum foundation. What does this mean for our cosmic speed limit? The prohibition we wrestle with today is built upon the classical spacetime of general relativity. It assumes a smooth, predictable fabric where light cones neatly define the possible and the forbidden. But if spacetime is emergent or discrete, then this entire elegant structure is a kind of macroscopic illusion, an average that emerges from a far more chaotic and interconnected quantum substrate. It is entirely possible, perhaps even likely, that a successful theory of quantum gravity will reveal pathways or phenomena that look like effective faster than light travel from our large-scale perspective. These would not be violations of a law, but operations on a deeper level of reality where the old law, as we formulated it, simply does not apply. The cosmic speed limit, in this light, begins to look less like a fundamental commandment etched into the universe and more like a signpost on a map. It warns us that the road ahead, as drawn by our current theories, ends in a mathematical cliff, but the map is not the territory. The true nature of the territory, the quantum structure of spacetime itself, remains largely uncharted. Our perceived prohibition might be the most profound misunderstanding of all, a limitation not of the cosmos, but of our classical imagination, forcing us to apply the rules of a smooth, continuous stage to a reality built from a quantum tapestry. The answer to whether we can reach the stars may not be found by breaking a rule, but by finally reading the universe's full instruction manual. The cosmos is a master illusionist, and one of its greatest tricks plays out across the vast emptiness of intergalactic space. From the hearts of distant quasars and active galaxies, colossal jets of superheated plasma erupt, stretching for thousands of light years. Within these jets, astronomers have observed something that should be impossible: bright knots of material that seem to race across the sky at many times the speed of light. This phenomenon, known as superluminal motion, is not a violation of Einstein's laws, but a breathtaking confirmation of them. It is a perfect example of a relativistic illusion, a trick of perspective and timing that reveals the true power of the theory. Imagine a single blob of plasma ejected from near a black hole at 99% of light speed and aimed almost directly at Earth. As this blob travels, it emits light continuously. The light emitted from the blob's position later in its journey has a slightly shorter distance to travel to reach us than the light it emitted at the starting point, because the blob itself is moving almost toward us. This compresses the arrival times of the light signals in our telescopes. We see the blob move from point A to point B in far less time than it actually took light to travel the true distance between those points in space. The result is an apparent velocity that mathematically exceeds the speed of light, sometimes by a factor of 10 or more. A Newtonian universe would have no explanation for this. It is only within the warped geometry of special relativity, with its time dilation and length contraction, that the numbers work out perfectly. This celestial sleight of hand teaches us a profound lesson about observation. What we perceive is not always the underlying reality. It is a projection filtered through the immutable laws of physics and the geometry of our vantage point. It forces us to be meticulous, to separate the artifact of measurement from the genuine property of the object, but it also sparks a deeper, more tantalizing line of thought. If nature can so easily produce such convincing phantoms of faster-than-light travel using only high-speed matter and clever alignment, what other illusions might be possible? Could the universe employ even more subtle geometries, perhaps involving the quantum foam or engineered spacetime, to create effects that are not illusory but genuinely effective? The existence of superluminal motion proves that reality has layers of complexity that can deceive even the most careful observer. It stands as both a cautionary tale and an invitation, a sign that the deepest truths of the cosmos may require us to look not just at what is moving, but at the stage upon which the motion is performed. Einstein himself grappled with a phenomenon so strange he famously called it spooky action at a distance. Today, we know it as quantum entanglement, and it is perhaps the clearest example of the universe permitting a connection that seems to defy our classical intuition about space. When two particles become entangled, their properties become inextricably linked into a single, shared quantum state. Measure one, and you instantly know the state of the other, no matter if it is across the room or across the galaxy. This correlation appears to happen instantaneously, suggesting a connection that operates outside the confines of light speed. For decades, this seemed like a direct challenge to relativity's cosmic speed limit. But the devil and the genius is in a critical detail. While the correlation is instantaneous, it is also completely random. You cannot force the entangled particle you hold to adopt a specific state in order to send a message to its partner. Any attempt to use entanglement for communication requires sending a second, ordinary message by classical means, at or below light speed, to explain what was done. It is like having two synchronized but randomly flashing lights separated by a vast distance. You see your light flash red, and you instantly know the other is red too. But you had no control over making it flash red to signal a prearranged message. To tell someone what the flash meant, you still have to call them on a radio, limited by the speed of light. This is the universe's elegant safeguard. It allows for a profound, non-local connection that seems to stitch reality together in a hidden layer, yet it meticulously erects a firewall to protect causality. No information, no signal, no cause and effect chain can be transmitted faster than light using entanglement alone. The universe appears to be forbidden in this very specific informational sense. Yet this very setup invites a deeper question. What is really happening in that instant of correlation? Our standard interpretation of quantum mechanics treats it as a purely mathematical link, with no physical mechanism traveling between the particles. But other interpretations dare to suggest a more tangible, if hidden, reality. Pilot wave theory, for instance, proposes that particles are guided by a real physical wave. In this view, the entangled particles are connected through this wave field, and influences within that field could, in principle, propagate faster than light in a hidden sub-quantum realm. This would not violate relativity in our observable world because the information in that hidden realm remains inaccessible for crafting signals. It is a stunning possibility. Our most successful theories, quantum mechanics and relativity, may only be describing the surface-level rules, the observable outcomes of a deeper, hidden game where connections are forged in ways we are only beginning to glimpse. The prohibition we perceive might simply be a feature of our current vantage point, a rule for players who cannot see the whole board. The universe is already performing the ultimate faster-than-light trick, and it is doing so on the grandest stage imaginable. Look out at the deepest fields of galaxies, and you are witnessing a cosmic magic act. The most distant galaxies we can see are not just moving away from us, they are receding at speeds that actually exceed the speed of light. This is not a theoretical speculation or an optical illusion like superluminal motion. It is a direct, measurable consequence of the universe's accelerated expansion, driven by the mysterious force we call dark energy. Here, the cosmic speed limit seems not just broken but utterly ignored. Yet, once again, Einstein's framework is not violated. It is operating on a different level entirely. Special relativity, with its strict local speed limit, governs motion through space, but what we are observing is not motion through space. It is the expansion of space itself. The very fabric of the cosmos between us and those distant galaxies is stretching, carrying the galaxies along with it like raisins in a rising loaf of bread. The farther away a raisin, the more dough between us, and the faster it appears to recede as the loaf expands. Beyond a certain distance, that cumulative stretching adds up to a recession velocity greater than light. This creates a profound and permanent boundary known as the cosmic horizon. Every galaxy beyond that horizon is already causally disconnected from us. The light it emits today will never reach us because the space it must cross is stretching faster than the light can traverse it. We are forever separated, not by a law of speed, but by the relentless geometry of an expanding universe. This presents a natural, observed example of a superluminal effect that is completely kosher within general relativity. The prohibition is not on speed, but on locally exceeding the speed of light through space. The stage itself, however, can grow at any rate it likes. This forces a staggering question upon us. If the universe can do this naturally on a scale of billions of light years, could the principles behind it be scaled down? Could a sufficiently advanced civilization learn not just to ride the geometry of spacetime, but to engineer it? Instead of building an engine to push a ship, they might build a device to deliberately stretch the space behind a vessel and contract the space in front of it, creating a controlled, local bubble of expansive and contractive geometry. This is not about breaking a rule. It is about learning to speak the universe's native language, the language of spacetime curvature. The cosmos is not showing us a forbidden act. It is demonstrating that the true rules of the game are written in the dynamic, malleable geometry of the vacuum. Our challenge is to move from being passive observers of this grand phenomenon to becoming active students of its deepest mechanics. That profound shift in perspective, from a static medium to a dynamic geometry, was not born in a vacuum. It emerged from the ashes of a beautiful, logical, and utterly wrong idea. For centuries, scientists believed light waves needed something to wave through, just as sound needs air. They envisioned a luminiferous ether, an invisible, stationary substance that permeated all of space, the stage upon which the drama of light played out. This ether was thought to be absolutely still, a fixed reference frame for the entire universe. If this were true, then the Earth, as it orbited the Sun, should be moving through this ether like a ship through a still sea. This motion should create an ether wind, a detectable difference in the speed of light depending on whether it was traveling with the wind or against it. In the late 19th century, two meticulous American physicists, Albert Michelson and Edward Morley, designed an exquisitely sensitive experiment to measure this effect. They split a beam of light and sent the two halves on perpendicular journeys, then brought them back together to create an interference pattern of light and dark bands. If the ether wind existed, it would slow one beam relative to the other, shifting this delicate pattern as they rotated their apparatus. They expected to see the fringes dance. They saw nothing. The pattern remained stubbornly, perfectly still. The ether wind was not there. This null result was not a minor setback. It was a full-blown crisis in physics. The most elegant explanation for how light worked had just been contradicted by the most precise measurement of its time. The stage everyone assumed was there simply did not behave as a stage should. Into this intellectual turmoil stepped a young patent clerk. Einstein's revolutionary insight was to take the problem and turn it inside out. Instead of trying to salvage the ether by adding more complex explanations, he asked a breathtakingly simple question. What if there is no ether at all? What if the speed of light is simply a constant, a fundamental feature of the universe that is the same for every observer, regardless of their own motion? To make this work, he had to let go of our deepest intuitions, absolute space and absolute time. Concepts that felt as solid as the ground beneath our feet had to be abandoned. In their place, he gave us a single, flexible entity, spacetime, where measurements of distance and duration depend on the observer's state of motion. The failed experiment was not a failure of detection. It was a clue pointing to a deeper, more elegant truth. the crisis was solved not by patching the old model, but by building a new reality from the ground up. This historical pivot holds a powerful mirror to our current dilemma with faster-than-light travel. Our firm conviction that it is mathematically forbidden feels as solid and logical today as the concept of the ether did to a 19th-century physicist. We are working within a paradigm, the magnificent edifice of relativity, and from inside that structure, the walls look absolute. But what if we are facing a similar kind of conceptual crossroads? The stubborn problems we hit, the infinite energies, the causality violations, they might be the modern equivalent of the unmoving interference fringes in Michelson and Morley's apparatus. They are not necessarily stop signs, but signals that we are asking the wrong question within an incomplete framework. The true breakthrough that allows us to reach the stars may not come from finding a clever way to exceed a speed limit within our current map of reality. It may require a shift as radical as Einstein's, a moment where we stop trying to make a faster spaceship and start redefining what travel even means. In a future physics, the concept of speed itself, of traversing a distance in a measured time, might become a secondary, emergent property. The primary concept could be something like quantum entanglement of spacetime geometry or conscious navigation of a multiversal landscape. We are so focused on the engine's thrust that we might be missing the shape of the road. The journey to the stars may not be a race, but a rearrangement. This cosmic isolation forces a deeper, almost philosophical question about the universe's architecture. Is the speed of light a fundamental law of nature, or is it a feature of a particular cosmic era? If it is absolute and unbreakable, then its implications are staggering. It transforms the galaxy from a potential community into a collection of isolated islands, each solar system forever quarantined from its neighbors by an ocean of time and distance. A civilization could blossom, create art, philosophy, and science for millennia, and its light, carrying the faint echoes of those achievements, would take centuries just to reach the next star. Any reply would take centuries more. In such a universe, meaningful contact becomes practically impossible. This profound isolation is a core ingredient in what we call the Fermi paradox. If the universe is so vast and old, and life is not impossibly rare, then the sky should be buzzing with activity. Yet we hear only silence. One compelling answer is that the silence itself is the answer. The light-speed barrier, combined with the mind-boggling scales involved, acts as the ultimate great filter. It does not wipe civilizations out, it simply cages them, making the galaxy a gallery of beautiful, lonely exhibits that can never meet. This view supports ideas like the rare Earth hypothesis, suggesting that complex life itself is a fragile miracle, and that the sheer difficulty of interstellar travel, bound by this universal speed limit, ensures civilizations remain forever separated. The laws of physics in this interpretation are not just rules, they are a cosmic quarantine protocol. But what if we have the causation backwards? Perhaps the universe is not designed to isolate, but our current understanding is designed to describe isolation. The prohibition we perceive might be a temporary condition, a feature of our current level of technological infancy. Think of a chick inside an egg. The shell is an absolute, unbreakable barrier from the chick's perspective. It defines its entire world and limits its possibilities. But that barrier is not a fundamental law of the cosmos. It is a temporary structure meant to be broken when the organism inside is ready. If faster-than-light travel is an engineering puzzle, not a physical impossibility, then the entire cosmic picture flips. The universe transforms from a prison of lonely islands into a navigable and potentially bustling archipelago. The silence of the Fermi paradox then becomes a question of timing or technology, or perhaps a choice to remain quiet. This dichotomy forces us to confront the nature of the laws themselves. Are the rules of physics arbitrary lines drawn in the sand of reality, or do they contain a deeper, almost logical purpose? One compelling idea is that they exist to preserve cosmic consistency. The potential for causality violation, the grandfather paradox, is so toxic to a stable, predictable universe that the laws may have evolved or been structured to prevent it at all costs. The speed of light limit would then be less like a wall and more like an immune system, a fundamental rule that prevents reality from developing logical infections. Another perspective is more biological. Could the light speed barrier exist to encourage biodiversity? On Earth, isolated ecosystems like islands or deep ocean vents evolve incredible, unique life forms. By limiting interaction between stellar systems, the universe guarantees that life and intelligence, if it arises, evolves along wildly different paths, creating a galactic tapestry of unimaginable diversity. Constant, easy contact might homogenize culture and thought. The barrier ensures that when or if civilizations finally do meet, they bring truly alien perspectives to the table. Our interpretation of Einstein's equations, then, is not a dry academic exercise. It is an act of philosophical storytelling that defines humanity's narrative arc. Do we see ourselves as permanent residents of a small, lonely oasis, destined to contemplate a universe we can never truly touch? Or do we see ourselves as pioneers standing on a shore, studying the ocean's currents and starting to design a vessel? The answer we choose shapes our vision of the future, our allocation of resources, and our very sense of purpose among the stars. It determines whether we look up at the night sky with a sense of tragic wonder, or with the focused gaze of an apprentice learning the first principles of a craft we one day hope to master. The search for cosmic neighbors now shifts from philosophy to forensic astronomy. If a civilization has learned to bend spacetime itself, their technology would not be subtle. It would leave scars on the fabric of the universe, signatures we could potentially see. Consider the theoretical mechanics of an Alcubierre warp drive in motion. As it travels, the warp bubble does not simply glide through empty space. It would sweep up the interstellar medium, the thin gas and dust between stars. These particles cannot cross the bubble's boundary, so they would become trapped and concentrated at the leading edge, a bit like cosmic snow piling up on a plow. Compressed to incredible densities and energies, this material would become highly unstable. The moment the drive decelerates and the warp field collapses, that accumulated energy would be released in a sudden, intense burst of radiation. Some models suggest this flash could resemble a form of Hawking radiation, a telltale spike across the electromagnetic spectrum with no natural astronomical source to explain it. It would be a technological thunderclap echoing through the void. The construction of such a device would be equally dramatic. To create the necessary spacetime curvature requires concentrating exotic matter or generating regions of negative energy density on a colossal scale. This is not a quiet process. The manipulation of spacetime on that level would produce unique gravitational distortions. Our telescopes already use a phenomenon called gravitational lensing to study dark matter and distant galaxies, where a massive object's gravity bends the light from behind it like a lens. A civilization assembling the components for a warp drive or stabilizing a wormhole would create a bizarre, localized lensing effect. It might appear as a strange, shimmering distortion in a patch of space with no visible massive object to cause it, or as a pattern of light that defies the smooth predictions of general relativity. Our sky surveys, like those conducted by the Vera Rubin Observatory, are already mapping the heavens in unprecedented detail. They are not just looking for planets, they are creating a dynamic movie of the sky, searching for anything that changes or moves in an unexpected way. A warp drive signature, whether a flash or a warp, would stand out as a profound anomaly. This reframes our entire quest. The mystery of faster-than-light travel moves from the chalkboard to the telescope. We are no longer just asking if the laws of physics permit it. We are asking if the universe shows evidence of it already being done. This transforms astronomy from a passive act of observation into an active detective hunt for the ultimate technological artifact. We are not merely searching for life, but for the fingerprints of a civilization that has graduated from manipulating matter to engineering the very stage of reality. The answer to our deepest question may not be hidden in the fine print of our equations alone. It could be written in the ancient light from a distant star, a flash of radiation that crossed the galaxy millennia ago, carrying the signature of a breakthrough we are only beginning to dream of. The silence of the cosmos might not be empty at all, but waiting for us to learn how to listen for the right kind of noise. That galactic-scale energy requirement was the ultimate reality check, a sobering splash of cold water on a beautiful mathematical dream. To build a single warp drive, you would first need to dismantle entire star systems, converting all that mass into the exotic, negative energy material required to bend spacetime. It was a showstopper, a numbers game that seemed to relegate the entire concept to the realm of pure theoretical fantasy, an elegant equation with no possible physical form. But science possesses a beautiful stubbornness. Researchers did not simply accept that first, brute force solution to the equations as the final word. They began to tinker with the geometry of the idea itself. What if the warp bubble was not a thick, rigid shell, but something far more delicate and dynamic? Subsequent calculations revealed that by shaping the warp field into an incredibly thin, oscillating torus, a kind of vibrating ring around the spacecraft, the negative energy requirements could be reduced not by a factor of 10 or 100, but by many orders of magnitude. The numbers plummeted from the mass energy of Jupiter to that of a small moon, and then, in some optimistic models, down to something on the scale of a modern spacecraft. This is a staggering conceptual leap. It transforms the problem from one of cosmic impossibility to one of profound engineering difficulty. The barrier is no longer a fundamental law written in stone, but a steep, technological mountain we have not yet learned to climb. Think of it like the history of computing. The earliest machines filled entire rooms with thousands of fragile vacuum tubes, consumed immense power, and performed calculations we would now consider trivial. They were the galactic-scale energy requirement of their day. The invention of the microchip did not change the fundamental laws of physics governing electrons, but it represented a revolutionary optimization in how we manipulated those laws. It made the impossible first possible, then manageable, then ubiquitous. The evolution of warp drive theory mirrors this path. Our first, clumsy solutions to Einstein's equations were the vacuum tubes. The refined, thin shell models are the early transistors. We have not yet found the equivalent of the integrated circuit for spacetime, but the trajectory of the idea suggests it may be a matter of ingenuity, not a violation of nature's rules. This shifts the entire conversation about faster-than-light travel. The question is no longer if the universe forbids it, but whether we can ever master the sublime engineering required to gently coax the fabric of reality into a shape that serves our journey. The energy problem begins to look less like a locked door and more like a complex lock, and we have just begun to understand the first, most basic principles of how a key might be fashioned. The most chilling argument against faster-than-light travel is not about energy but about story. It suggests that superluminal motion, through the twisted geometry of spacetime, could forge a bridge not just between places but between times. This creates what physicists call a closed time-like curve, a path through the cosmos that loops back to its own beginning. Step onto such a path and you become a time traveler. This is where logic itself seems to unravel, giving rise to the terrifying specter of paradox. The classic example is the grandfather paradox, a thought experiment where a traveler goes back in time and prevents their own grandfather from meeting their grandmother. If that happens, the traveler is never born, so they could never have taken the trip to begin the interference. It is a perfect, maddening circle of contradiction that seems to prove such journeys must be impossible, for they would allow reality to contradict itself. But what if our understanding of possibility is too narrow? One profound resolution to this nightmare comes from the mind of Russian physicist Igor Novikov. He proposed the self-consistency principle, a radical idea about how the universe might handle these loops. Novikov suggested that the laws of physics simply do not permit paradoxes to occur. The timeline is not a fragile thread that can be snapped, but a single, immutable, and self-consistent story. If you were to travel into your own past, any action you took would not be a change, but always already a part of that past. Your attempt to create a contradiction would be subtly, perfectly thwarted by reality itself. The gun you meant to fire would jam at the crucial moment. The vital message you tried to send would be lost in the static. The path you walked would be the only path that could have led to you being there in the first place. In this view, causality is not a chain you can break, but a pattern you are woven into. You cannot change the past because you, the traveler, are a product of that very past. Your journey is not an intrusion, but a completion. This principle transforms the grandfather paradox from a logical impossibility into a physical impossibility of execution. The universe does not necessarily forbid the act of traveling along a closed time-like curve. Instead, it might rigidly enforce narrative consistency on anyone who tries. Think of it like an author writing a complex novel with time travel. A skilled author ensures every event in the past logically leads to the traveler's arrival, and the traveler's actions in the past seamlessly cause the future they came from. The story has no plot holes because the author makes it consistent. Novikov's principle suggests the cosmos itself is that ultimate author, with the laws of physics as its editorial rules. This has a stunning implication for our search for faster-than-light travel. The ultimate barrier may not be a prohibition on the geometry itself, but a deeper law of cosmic coherence. A sufficiently advanced civilization might indeed learn to fold spacetime into a ring, creating a shortcut that is also a time loop, but upon stepping through, they would find their freedom curiously constrained. They could observe, they could interact, but they could not create a logical inconsistency. Their every move would be channeled into actions that preserve the one unified timeline. The universe might allow the technology, but it would demand perfect storytelling from those who use it. This shifts the goalposts entirely. The challenge is no longer just about bending space or gathering exotic matter. It becomes a challenge of alignment, of navigating a path where every choice you make is the one that already was made. It suggests a cosmos that is less like a machine with rigid rules and more like a grand, self-correcting narrative, where even our most audacious attempts to rewrite the plot are seamlessly absorbed into the tale. Theoretical breakthroughs are one thing, but can we touch these ideas even in a small way? Remarkably, the answer is yes, and the laboratory for these first experiments is not a particle accelerator, but a tabletop. Scientists are now building devices that don't just calculate spacetime curvature, but actually mimic its effects using entirely different physical systems. This emerging field is called analog gravity, and it operates on a powerful principle that the mathematical equations describing wildly different phenomena can be strikingly similar. The flow of a fluid down a drain, for instance, can be described by equations that mirror those for matter falling into a black hole. By creating a carefully controlled vortex in a superfluid, researchers have been able to detect faint signatures analogous to Hawking radiation, the theoretical glow emitted by black holes. They are not creating real black holes, of course, but they are creating an environment where the same kind of physics plays out, allowing us to test our theories in a beaker. This is a profound shift from pure thought experiment to tangible, if tiny, physical model. we are learning the grammar of extreme gravity by listening to its echoes in other materials. Another frontier lies in metamaterials, human-engineered substances with properties not found in nature. These are not defined by their chemistry, but by their microscopic structure, like intricate lattices or repeating patterns etched at scales smaller than the wavelength of light. Just as a prism bends light, a metamaterial can be designed to bend electromagnetic waves in precise, exotic ways. Researchers have used this to create devices that function as optical black holes, capturing and absorbing light waves in a manner that mimics an event horizon. Others have designed invisibility cloaks that guide light around an object, effectively removing it from view by manipulating the path of light, not unlike how massive objects warp the geodesics of spacetime. These are not toys, they are functional analogies, physical demonstrations that the geometry of space can be engineered, at least for certain kinds of waves. None of this breaks the speed of light or creates a wormhole, but that is not the point. These experiments are the very first, painstaking steps in what might one day become an engineering discipline of spacetime itself. They are the equivalent of the first humans who rubbed sticks together to make a spark, long before anyone conceived of a steam engine. We are learning to recognize the raw materials and the basic principles of a force far more profound than fire. If we can learn to convincingly mimic the effects of gravity with light and sound and super-cold fluids, we are mapping the territory. The next, almost unimaginable step would be to ask if we can induce those effects controllably, not as an analogy in a lab material, but in the vacuum of space itself. We are moving from simulation toward a distant, shimmering possibility of realization. Our drive to reach the stars is written in our oldest stories. Long before we understood the physics of light, we dreamed of crossing impossible distances, from Homer's wine-dark sea to Jules Verne's journey to the moon. These narratives are not just entertainment, they are the blueprint of our curiosity. They define what it means to be human, to push against boundaries and seek connection beyond the horizon. A cosmos permanently bound by light speed presents a profound narrative crisis for a species like ours. It would mean that the greatest story we can ever tell is confined to a single, tiny neighborhood in an unimaginably vast city. Every epic we write, every saga we imagine would ultimately be a local tale. The heroes could never sail the sea of stars, only gaze at its unreachable shores. This is a deeply unsatisfying ending for a storytelling animal. It feels less like a law of physics and more like a tragic flaw in the plot of existence itself. This powerful longing shapes the scientific conversation in subtle but undeniable ways. It makes the word forbidden feel like a challenge, and the word misunderstood sound like hope. When a physicist publishes a paper on warp drive metrics or negative energy, it resonates far beyond academic circles because it taps into this deep cultural vein. We are not neutral observers of these equations. We are participants rooting for a universe that has a secret door, a hidden clause, a way for the story to continue. This psychological bias does not make the science any less real or rigorous, but it is crucial to acknowledge its presence. It is the reason a difficult engineering problem can feel like a cosmic injustice, and a theoretical loophole can feel like a promise. Our interpretation of the evidence is filtered through a profound desire to not be alone, to not be silent, to have a stage grand enough for the epic we feel brewing in our collective soul. Recognizing this bias is not a dismissal, it is a step toward clearer thinking. It allows us to separate the cold, beautiful logic of mathematics from the warm, driving force of myth. We can admire the elegant impossibility in one set of equations while diligently searching for a more permissive set, not out of childish defiance but with clear-eyed purpose. This human element is itself a critical piece of the puzzle we are trying to solve. The mystery of faster-than-light travel is not just about space-time curvature and quantum foam. It is also about the strange, persistent creature asking the question, a creature that seems biologically and culturally wired for journeys it cannot yet make. Our longing is data. It tells us something about what we expect from the universe, rightly or wrongly. It suggests that our science and our stories are two languages describing the same deep truth, that to be alive is to move, to explore, and to connect. Whether the cosmos ultimately humors this ambition remains to be seen, but the ambition itself is a fundamental part of who we are, lighting the way forward as surely as any star. That deep human longing for a navigable universe forces us to question the very bedrock of our cosmic map, the constants themselves. We have built our understanding of reality on the assumption that numbers like the speed of light are fixed, unchanging pillars. But what if those pillars were not always so rigid? A small but influential group of cosmologists, including Joe Megiddo, have pursued a radical line of thought known as variable speed of light theories. These VSL models propose that in the searing heat of the first moments after the Big Bang, the speed of light was not the constant we measure today, but was vastly, perhaps infinitely higher. This is not a minor tweak, it is a fundamental reimagining of cosmic dawn. The primary motivation for these ideas is to solve the same profound puzzles that the more mainstream theory of cosmic inflation was designed to address, like the horizon problem, which asks why opposite sides of the observable universe are so uniform in temperature when they seemingly never had time to exchange information. Inflation solves this by proposing a period of ultra-rapid expansion, stretching a tiny, connected region into our vast cosmos. Variable speed of light theories offer a different solution. If light moved incomprehensibly fast in that early epoch, then distant regions could have been in thermal contact after all, establishing uniformity before the speed settled down to its current value. While these models typically describe a change in the fundamental constant over cosmological time, across billions of years, and not a dial we can turn locally in a lab, their philosophical impact is immediate and profound. They demonstrate that the constancy of the speed of light, the great C in all our equations, is a postulate, a foundational assumption of our current physics. It is incredibly well tested and verified in our present era, but we have no direct observational proof that it has always been the same number throughout the entire history of the universe. The possibility that the rules themselves can evolve challenges our deepest intuition about the laws of nature. We tend to see them as eternal, handed down from some cosmic legislature at the beginning of time. But if a fundamental constant like the speed of light can change, then the laws are more like a narrative, a story that unfolds and develops along with the cosmos itself. This speculative frontier leads to an even more tantalizing question. If the speed of light could be different under the extreme energies of the early universe, could there be other extreme conditions, perhaps involving densities beyond our comprehension or states of matter we have not yet conceived, where the local value of C is effectively different? Could a sufficiently advanced technology create a localized environment that mimics those primordial conditions, not to change the universal constant, but to create a bubble where physics operates with a different set of rules? This remains firmly in the realm of speculation, far from any testable engineering. But the value of these theories is not in providing a blueprint for a star drive. It is in the powerful reminder they offer. Our laws of physics are not absolute truths etched on a cosmic tablet. They are a magnificent, self-consistent description derived from observations made within a specific cosmic era, under a specific range of conditions. They are the language we have learned to speak in our particular neighborhood of reality. To assume that language has no dialects, no historical changes, and no exceptions is to mistake the map for the uncharted territory that still lies beyond its edges. This leads us to the outermost edge of speculation, where physics meets philosophy in the digital realm. The simulation argument proposes a startling possibility. that our universe, with all its galaxies, laws, and conscious beings, is not base reality, but an immensely sophisticated construct, a digital simulation running on some unfathomable computer. In this view, the laws of physics we strive so hard to decode are not fundamental truths of nature. They are the programmed rules of the simulation, the underlying code that governs how the program renders reality for its inhabitants. The speed of light, then, is not a cosmic constant etched into the fabric of spacetime. It is a parameter, a line of code set by the architects of the simulation. Why would such a limit exist? Perhaps for purely practical reasons, to optimize the processing power required to simulate a vast universe in real time. Calculating the interactions of every particle across interstellar distances is computationally expensive. Enforcing a universal speed limit creates a kind of buffer, a maximum rate at which information needs to be processed and causality needs to be resolved. It keeps the simulation from crashing under its own complexity. Or the limit could be a narrative constraint, a rule built into the simulation to ensure a coherent, stable experience for the entities within it, preventing paradoxes and preserving a linear flow of events. From this digital vantage point, the dream of faster-than-light travel takes on a completely new character. It would not be about bending space-time or gathering exotic matter. It would be about hacking the system. Achieving FTL would be equivalent to finding an exploit in the code, a backdoor that allows you to bypass the standard rendering process. Think of a video game where a character is supposed to walk from one city to another across a vast landscape. The game engine calculates every step, renders every tree and rock along the way. But a player who discovers a cheat code can simply teleport, inputting a command that instantly moves their character's data to the new coordinates without the game processing the journey. In a simulated universe, superluminal travel might work the same way, not moving through space, but updating your location data in the Universal Registry, or accessing a developer console that lets you skip the computationally intensive steps. This is, of course, the purest form of science fiction and philosophical exercise. There is no test, no experiment we can currently conceive to prove or disprove the simulation hypothesis. Yet its value is not in providing a practical path to the stars, but in the profound perspective shift it forces upon us. It asks us to consider that a fundamental prohibition in one layer of reality might be nothing more than a software limitation in another. The wall we keep hitting may not be a wall at all, but the edge of our user permissions. This thought experiment dissolves the distinction between a law of nature and a line of code, challenging the very essence of what we mean when we say something is forbidden by physics. Are we trying to break a universal law, or are we merely trying to understand the user interface well enough to find the hidden menus? It reframes our entire quest from one of cosmic engineering to one of cosmic debugging, a search not for a loophole in nature, but for the source code of reality itself. The strangest frontier in our search may not be out in the cosmos, but within the mind itself. Quantum mechanics, our most successful theory of the very small, presents a puzzle that has never been fully resolved. In the classic Copenhagen interpretation, a particle does not have a definite position or state until it is measured, until an observation is made. This act of measurement, some argue, requires a conscious observer to collapse the wave function from a haze of possibilities into a single, concrete fact. This places consciousness not as a passive byproduct of the brain, but as an active participant in shaping reality. It is a deeply controversial idea, far from mainstream physics, yet it opens a door to a breathtaking possibility. If consciousness is somehow fundamental to the fabric of reality, could its nature be non-local, not confined to the space inside our skulls? Could it perceive or interact with the universe in a way that transcends the speed of light? This is not about building a faster ship, but about questioning the very nature of the traveler. For decades, researchers at the Princeton Engineering Anomalies Research Lab explored this fringe. They conducted experiments where human participants attempted to mentally influence the output of truly random number generators, machines that produced nothing but electronic noise. Their statistical analyses, debated fiercely to this day, suggested tiny but persistent deviations from pure chance when focused intention was applied. The effects were minuscule, but the implication was monumental that mind and matter might share a subtle, non-physical link. If such a connection exists, however faint, it hints at a layer of reality where information is not transmitted through space, but is simply present, accessed through a faculty we do not yet understand. From this speculative vantage point, the light-speed barrier begins to look like a feature of our current mode of existence, a rule for objects and signals moving through spacetime. But what if consciousness itself operates on a different set of rules? The barrier might not be in the machinery of the universe, but in the limitations of our own perceptual apparatus. We are like deep-sea creatures who perceive the world only through pressure and chemical senses, utterly unaware of the vast electromagnetic spectrum shimmering above the waves. Our entire concept of travel is built on the idea of moving a physical body from point A to point B across a distance. But if awareness is non-local, then travel might be the wrong word entirely. The next evolutionary step for a spacefaring civilization might not be an engine, but an expansion, a learned ability to shift the focal point of consciousness itself. Imagine knowing a distant star not by waiting centuries for a probe's signal, but by a form of direct, non-local acquaintance, as instantly as you know your own hand. This is not mysticism, but a logical extension of the hardest problem in science, the problem of subjective experience. Our current physics vocabulary has no terms for this. It can describe particles and fields and spacetime curvature, but it has no equations for awareness. The prohibition we perceive against faster-than-light travel might be the ultimate misunderstanding, a confusion between the map of physical objects and the territory of conscious experience. We have been trying to solve a puzzle of distance with tools of distance, when the solution might lie in realizing that from a certain perspective, there is no distance to cross at all. The ultimate engine for the stars will not be forged from steel or powered by fire. It will be built from substances that currently exist only in the most speculative corners of physics, materials that do not just exist in space, but actively sculpt the geometry of spacetime itself. The bridge between a beautiful equation on a chalkboard and a functional warp bubble is a chasm of material science so vast it redefines the word engineering. Think of the history of computation. The theoretical concept of a programmable machine existed for centuries, but its realization required the painstaking discovery of silicon, the mastery of semiconductor physics, and the ability to etch circuits smaller than a wavelength of light. That was the material revolution that built our digital age. A similar but far more profound revolution awaits any civilization aiming to build with spacetime. The equations tell us what we need, a substance capable of generating and sustaining regions of negative energy density, a kind of anti-gravity glue to hold open a wormhole throat or shape a warp bubble's boundary. This is not merely a rare element or an unusual alloy. It is a state of matter that pushes against the vacuum itself. We catch glimpses of its possibility in laboratory curiosities. A Bose-Einstein condensate, where atoms chilled to near absolute zero merge into a single quantum wave, exhibits behaviors utterly alien to our everyday world. Could such a condensate, scaled to macroscopic size and stabilized with inconceivable precision, be tuned to influence the local properties of the vacuum? Even more extreme are theoretical constructs like quantum froth, the seething foam of virtual particles thought to make up spacetime at the Planck scale, a distance a trillion times smaller than an atom. To engineer at that level would be to move from building with bricks to building with the very concept of substance. This suggests a staggering timeline. Our journey may not hinge on a single, blinding flash of insight from a lone genius, like Einstein's revelation about relativity. Instead, it might unfold as a gradual, collective ascent up a mountain of material mastery. 1 century might bring the stabilization of macroscopic quantum states. Another might achieve the first, fleeting creation of a microscopic region of engineered vacuum. Millennia later, a civilization might learn to weave those regions into stable structures. Each epoch would unlock a deeper layer of control over a more fundamental aspect of reality, turning the seemingly magical into the merely technical. From this vantage point, the famous prohibition against faster-than-light travel begins to look different. It is not a cosmic edict stamped on the universe. It is a reflection of our current position on that technological timeline. We are in the earliest chapters of the story, still learning to work with the crude materials of our planetary cradle. The laws of physics do not say never. They simply outline the rules of a game whose most advanced levels require tools we have not yet invented, materials we have not yet conceived, and an understanding of reality we have only just begun to pursue. The barrier is not against the potential of intelligence, but a measure of our own technological infancy. Mastering the stars would demand more than equations and exotic matter. It would require a wisdom we have yet to prove we possess. The sheer power to bend spacetime and cross interstellar voids in a heartbeat is not merely a transportation breakthrough. It is a civilization-ending weapon and a profound ecological hazard. Consider the grim arithmetic of conflict. On Earth, the distance between nations created a buffer, a time for diplomacy and second thoughts. An interstellar civilization with instantaneous travel loses that buffer entirely. A grievance or misunderstanding could escalate into a war spanning light years in the blink of an eye, with weapons capable of manipulating the fabric of reality itself. The concept of a front line vanishes, replaced by the terrifying possibility of an attack materializing without warning from any point in space. The technology that promises to unite a galaxy could just as easily shatter it into permanent, paranoid fragments. Beyond conflict lies a quieter, more insidious danger: biological and ecological contamination. Every world is a unique experiment in evolution, a closed ecosystem that developed in splendid isolation. Our own planet's history shows the catastrophic disruption that can occur when species are introduced to new environments. Now imagine that on an interstellar scale. A single microbe, harmless in its home biosphere, carried on the hull of a ship or in the breath of a traveler, could become an apocalyptic plague on a world with no natural defenses. We could unintentionally become the agents of a galactic extinction event, wiping out nascent life or complex ecologies we never even knew existed. The responsibility is staggering, a burden of care that must be woven into the very design of any faster-than-light technology, from decontamination protocols to the ethical principle of non-interference. This leads to a chillingly elegant interpretation of the cosmic speed limit. Perhaps the barrier is not a physical prohibition at all, but a developmental filter. The universe may not forbid the engineering of spacetime. It may merely place that knowledge behind a test of maturity. Solving the physics puzzle grants you the keys to the galaxy, but only if you have first solved the deeper puzzles of sociology, ethics, and collective wisdom. A species still divided by tribalism, driven by short-term greed, or unable to steward its own planet would find such power to be a suicide pill. The light-speed barrier, in this view, is the universe's ultimate safeguard, a cosmic child lock preventing a volatile young civilization from accidentally burning down the stellar neighborhood before it grows up. Therefore, our quest for the stars becomes a dual endeavor: Every calculation about negative energy densities must be paired with a conversation about cosmic responsibility. Every experiment in analog gravity should be accompanied by a commitment to fostering global cooperation and foresight. The final challenge may not be in a laboratory, but in our own hearts and institutions. Can we transition from a species that exploits its environment to one that nurtures it? Can we resolve our conflicts through dialogue rather than destruction? Can we think in time frames that span centuries, not just election cycles? The answers to these questions may be the real prerequisite for the physics to even become possible. The silent cosmos we observe might not be empty. It might be waiting, listening not for our radio signals, but for the echo of our own maturity, the proof that we are ready to join a community we cannot yet see. The universe we perceive might be a single page in a vast multidimensional library. This is the startling vision offered by modern string theory and its extension, M-theory. It suggests our entire cosmos, with all its galaxies, stars, and planets, is not the whole story. Instead, it could be a three-dimensional membrane, or brane for short, drifting within a higher dimensional expanse called the bulk. In this radical picture, the three spatial dimensions we move through are not all that exist. They are simply the dimensions confined to the surface of our particular brane. The bulk contains additional spatial dimensions, curled up or extended, that are invisible to us because all the particles and forces we know of are stuck to our brane like ink on a page. This is not just a mathematical curiosity. It redefines the very meaning of distance. 2 points that are incredibly far apart on the surface of our brane might be surprisingly close if you could only step off the page and move through the bulk. Imagine a single sheet of paper representing our universe. Draw 2 dots on opposite edges. For an ant confined to the flat surface, the journey is a long, straight line across the entire page. But if you fold the paper, bringing those 2 dots almost touching, the ant's journey is now impossibly short, provided it can do something extraordinary, lift off the surface and step through the third dimension to the other dot. In the brane and bulk model, faster-than-light travel is not about breaking a speed limit on the page. It is about discovering that the page is folded in a higher dimensional space and learning how to make that short hop through the bulk. From our perspective inside the brane, a ship that did this would vanish from one point and reappear almost instantly at another, seemingly having moved faster than light. Yet locally on its path through the bulk, it may never have exceeded the speed of light. The cosmic rule remains intact, but the map of reality has just gained entirely new continents. The challenge, of course, is monumental. How do you access a dimension you cannot perceive? The particles that make up our ships and our bodies are bound by forces that keep them glued to our three-dimensional brane. To detach and move into the bulk would require energies of an almost unimaginable scale, at the level of the Planck energy, or a fundamental understanding of how to manipulate the very geometry of these extra dimensions. It would be like trying to teach a drawing on a sheet of paper to become self-aware, peel itself off the surface, and float into the room. Yet, this framework transforms the dream of interstellar travel from a problem of propulsion into one of dimensional architecture. We are not trying to build a faster engine, we are trying to find the door to the next room. The universe, in this view, is not a lonely island in a void. It is one apartment in an impossibly vast multidimensional complex. The silence of the cosmos might not mean our neighbors are absent, but that we are all living on different floors, unaware of the hallways that connect us. Our search for a way to the stars becomes a search for the blueprint of the building itself, a quest to understand not just the laws of our own apartment, but the layout of the entire cosmic skyscraper. Perhaps the ultimate reason we perceive a cosmic speed limit is because we are here to perceive it. This is the startling logic of the Anthropic Principle. a perspective that shifts the question from why the laws are what they are to why we see the laws that we do. It proposes a profound selection effect. The universe we inhabit, with its specific constants and rules, is not necessarily the only possible configuration. It is simply one that allowed for the emergence of stars, planets, and eventually conscious observers like us. Consider the chain of events necessary for our existence. It required a stable universe that lasted billions of years, where stars could form, fuse elements, and die, seeding space with the carbon, oxygen, and iron that make up our world and our bodies. It required planets with stable orbits and climates that could nurture the slow, delicate process of evolution. Now imagine a different universe, one where faster than light travel is trivial, as easy as stepping onto a train. In such a cosmos, the fundamental stability we take for granted might evaporate. The ability to move faster than causality could allow tiny fluctuations from the universe's fiery birth to propagate wildly, preventing the smooth, even distribution of matter needed for galaxies to form. Or it might enable paradoxes that unravel timelines, making the long, consistent history required for life's development an impossibility. In those hypothetical universes, stars might flicker and die young, planets might never coalesce, or the fabric of reality itself might be too turbulent for complex chemistry to ever begin. There would be no astronomers in those realms, no physicists gazing up at the night sky and wondering why they cannot go faster. They would be empty of observers altogether. We find ourselves in a universe where light speed seems like an absolute barrier precisely because this is the kind of stable, orderly cosmos that could eventually produce beings capable of contemplating the barrier. The apparent prohibition is not a fundamental commandment etched into the void. It is more like a feature of our particular cosmic habitat, a necessary condition for the story we are a part of. This reframes our entire quest. We are not battling against an arbitrary rule. We are exploring the very boundaries of the stable environment that allowed us to exist. Attempting to achieve faster than light travel, then, becomes an experiment in pushing the limits of our cosmic habitat. Could we create a localized, controlled exception to the rule without triggering the instability that would make our existence impossible in the first place? Or does any successful method inevitably require altering the foundational stability we depend on? The anthropic perspective suggests the laws we seek to bend are not just rules of a game, but the walls of our nursery. The silence of the cosmos may not be a sign of emptiness, but of a profound and necessary quiet, the deep stillness that allows a fragile, curious flame like consciousness to ignite and, against all odds, begin to wonder about the nature of the darkness. Perhaps the most radical perspective of all suggests that everything we see and touch is not the foundation of reality, but a consequence of something far more fundamental. Some theorists propose that the universe is not made of matter or energy in the primary sense. Instead, they argue that information is the most basic substance of existence. In this view, what we perceive as particles, forces, and even the curvature of spacetime are not the starting points. They are emergent phenomena, like a three-dimensional movie projected from a two-dimensional code. This idea, sometimes called digital physics or constructor theory, reframes the cosmos not as a grand machine, but as an unfathomably complex computation. The laws of physics become the algorithms of this cosmic program, and the constants of nature, like the speed of light, are not arbitrary numbers. They are parameters set by the system's architecture. From this vantage point, the cosmic speed limit takes on a completely new meaning. It might not be a barrier in space at all, but a reflection of a deeper informational constraint. Think of it as the maximum clock speed of the universe's processor. Just as your computer has a limit to how many calculations it can perform per second, the underlying computational substrate of reality, might have a maximum rate at which information can be transmitted, processed, and rendered into the consistent world we experience. That maximum rate, the theory suggests, is what we measure as the speed of light. It is the universe's bandwidth limit. This transforms the dream of faster-than-light travel into a completely different kind of problem. It would not be about building a more powerful engine or finding a loophole in spacetime geometry. It would be akin to finding a cheat code in a video game, a way to bypass the standard rendering process of the simulation. Or more ominously, it might be equivalent to forcing a processing error, a glitch that could corrupt the local reality around you. The goal shifts from physical engineering to a form of cosmic programming. Understanding reality at this level would be like learning the assembly language of the cosmos, moving from using software to reading the raw source code. Could such a code be hacked or optimized? We have no idea. The very concept pushes at the edge of scientific philosophy, but the value of this perspective is not in providing a blueprint. It is in the profound shift it forces upon our imagination. It suggests that the ultimate mastery of the stars may not begin with a telescope or a particle collider, but with a new kind of logic, a mathematics of existence that treats information not as something we record about the world, but as the very stuff the world is made of. Our journey through this labyrinth of light and law leaves us not with a simple answer, but with a transformed question. The cosmic speed limit is not a monolithic forbidden sign stamped across the universe. It is a complex border, a checkpoint between different realms of physical possibility, defined by the delicate interplay of energy, causality, and geometry. From one perspective, the prohibition is absolute. Within the pristine, flat spacetime of special relativity, pushing any object with mass to light speed demands infinite energy and leads to mathematical impossibilities. That wall is real and unyielding for the rockets and particles of our current world. Yet, step back and view the cosmos through the lens of general relativity, and the landscape shifts dramatically. The wall becomes a feature of the terrain, not an eternal decree. By manipulating the very fabric of spacetime, folding it into wormholes, surfing it on warp waves, we glimpse pathways where the journey's length, not the traveler's speed, becomes the variable. Here, the light-speed barrier is not broken. It is masterfully circumvented by redefining the map itself. This dazzling loophole, however, comes with its own profound requirement, a substance with negative energy to hold the shortcut open. This exotic matter is not a fantasy. It is a whisper from the quantum vacuum, a real phenomenon observed in the subtle pressures of the Casimir effect. The universe's own rulebook permits the ingredients, but gathering them on a useful scale remains a challenge of almost unimaginable engineering. This tension points to the grand synthesis still awaiting us, a theory of quantum gravity. Our current understanding is split, with relativity governing the vast stage and quantum mechanics dictating the frenetic dance of the particles upon it. Until these two magnificent theories are united into a single, coherent description of reality, our question about faster-than-light travel remains provisional. We are trying to solve a puzzle with only half the pieces. For now, the question stands not as a final verdict, but as an open invitation. It invites us to deepen our understanding, to challenge our most cherished assumptions about space, time, and motion. It asks us to look at the stars not as distant, unattainable prisons, but as the ultimate puzzles waiting to be solved. The universe may not forbid the journey to other suns. It may simply demand a wiser, more patient, and infinitely more creative traveler. What do you think lies beyond this luminous frontier? Share your thoughts on this cosmic conundrum below, and join us as we continue exploring the universe's greatest mysteries.